So we have our next speaker, Kailash Nadh, who will be joining us today. He is the founder at FOSS United, CTO of Zerodha. He'll be talking about 7 plus million Postgres tables. The talk explores how they use a single node Postgres to have more than 7 million ephemeral tables as a caching strategy for serving reports from a trillion row database to millions of users on daily basis at Zerodha. Give it up a huge round of applause for Kailash. Thank you so much.
Good evening. So I'm going to be talking about a hack that we built at Zerodha. It started out as a hack, but it's gotten out of hand. It's become a really large system that the organization depends on. A lot of the scaling that we do with financial reporting depends on it. And it also involves software abuse. So when I was preparing these slides, I realized last year I gave a talk here, and it was about abusing DNS. DNS is used for querying domain names. But I had this hack where I got DNS to deliver weather data, temperature data, all kinds of random stuff. And it worked, but it was proper abuse. And while making these slides, I realized here I'm going to talk about abusing Postgres. Battle-hardened, amazing piece of software, but abusing Postgres and doing stuff with it, which it wasn't really designed for, I guess. For whatever reason, that's 2 consecutive years of software abuse. So very large databases exist in a lot of places. It exists in the government, it exists in businesses, banks have it, stockbrokers have it, all kinds of places. And the velocity of data, the nature of data also varies. You have new data that is added to it, new transactions, and old data is archived to, cold storage data warehouses, etc., etc. So there's that whole distinction of hot data, cold data, and whatnot. OLTP versus OLAP. We had a bunch of OLTP versus OLAP discussions here earlier today. And if you are a people-facing organization or a business or a project, people need reports. You log into your bank, you pull net banking reports. You log into your e-commerce platform, you pull up your order history. Sometimes you need a bank statement from 10 years ago. Most times, like 99% of the people, 99% of us, we need reports, events that have happened in the recent past, last week, last year, last financial year. But if you think of the backend, if you think of the database in itself, all of this data is going and sitting somewhere, right? Millions, billions, even trillions of transactions. There are no database systems that can hold unlimited amounts of data and quickly deliver reports from 10 years ago, scanning back, 500 billion rows versus today. So generally data gets moved out of databases into shards, warehouses, etc. You would have noticed that some banks, actually most net banking systems, have different UIs or different menus for downloading different kinds of reports. One UI, one menu for downloading this financial year's report, and you have to go to some obscure menu to download some other report from an older period. That's because they probably have entirely different databases and backends just serving those old reports. And very large DBs are slow. It doesn't matter if you use Postgres, if you use ClickHouse, if you have 100 billion rows like we do, or hundreds of billions of rows, and if you have cross-table joins, it's going to be slow. So at Zerodha, millions of users come and download different kinds of millions of different reports every day. Some reports are as simple as, and when I say reports, I'm talking about databases, flat tables, and us using SQL queries to pull those reports, just like any other organization. So some of those reports are really simple. It's just a simple select statement, indexed fields, boundary of 2 dates, and you pull data. That is instant. But some reports are really complex. There are hundreds of lines of SQL, hundreds of 10 different joins, cross-table joins, sometimes even cross-database joins. Those queries can take 10 seconds, 20 seconds, 30 seconds. Now imagine on the tax filing day, you have 2 million people come onto your website or web app or whatever, and they all want to download last year's statements. And these statements involve hundreds of joins. And these statements have to be pulled from databases with hundreds of billions of rows. How will that scale, right? You're getting tens of thousands of requests of people pulling reports from these large databases per second. So there are many ways of scaling databases. Generally, you just copy the database, you keep on adding read replicas, you send queries to pull data, but that's expensive and non-viable when you have really large amounts of data. Each of those databases are like 10, 20, 30 terabytes, whatever. So what I just described is the synchronous way of pulling data, pulling reports. Somebody comes and clicks a button saying get report. That request goes from the browser or wherever to an app. That app opens a database connection, issues an SQL query, waits for it, and then the data comes back to the app. Then the data is sent back to the user. And like I said, some of these queries can take tens of whatever seconds. And at any moment, each of these open connections are waiting, holding up resources, hammering the database. So synchronous generation of reports, which is basically large, complex SQL queries, that's simply not viable. It just doesn't scale. This is how it generally looks like. N number of users come to your app. They all click on a button saying, give me my report. Each request becomes a query to the database, N number of queries, and the app is waiting on the database, and the user is waiting on the app, and it snowballs and everything goes for a toss. So there are many ways of, many different tricks, techniques, many different architectures of handling this. But I think pretty much all of those architectures involve asynchronous queuing and controlling. 10 million people come to your website, they all press that one get report button. But instead of sending those 10 million requests to the database, the large, slow database in the backend, they go sit in a queue somewhere, asynchronously. Then those queries are sent to the database one by one based on how much the database can handle, and the responses come back and they sit somewhere. And they're presented to the user in an asynchronous manner. Citing my bank example earlier, if you go to your net banking UI and download a very old report, typically when you click download, it says something like, your report is being generated, come back later. That's because this asynchronous thing is happening. And there's nothing new in this. This is not rocket science. This is a very, very ancient technique. So this is how that would look like. Rather than sending every single request to the database directly, which it can't handle, you asynchronously queue it somewhere and slowly send it to the database. The user waits or the user comes back and it's presented on the user's UI. Now the thing about that technique is that in an organization, in a setup like Zerodha, you have many different applications that are all written in different languages with different database drivers. You have many different kinds of databases. We have MariaDB, Postgres, ClickHouse. Different data resides in different databases for whatever reasons, like legacy reasons. So hard coding all of this logic, queuing, pooling, asynchronous queue management, etc., into each and every application, which can be built or written in any language or framework, that's not viable. You'll end up reinventing the wheel over and over. It's simply not viable. And if you end up doing that, suddenly you are mixing the heavy reporting layer, which involves large databases, which is a whole different scaling problem. You're going to tightly couple that into your application layer. Now your app can't scale independently, your database and queries and reporting can't scale independently. So what if there was an independent middleware, where this middleware system, it received all the requests for all report generation. It handled it, stored it. It did traffic control, and the system queries the slow, large database based on how much it can handle and manages the state of each pending request and delivers the response back to the app via an intermediate results DB. So I think this is, like I said, the asynchronous queuing bit is not new. Everybody does it. But I think this results cache is it's an interesting hack which is novel in this technique that we've tried. So we have a results DB. It's a Postgres instance, I think. Yeah, I'll come to it. So it's a Postgres database. And the large, slow databases are Postgres, ClickHouse, whatever. Hundreds of billions of financial records. And they have limited capacity to handle queries. So we have this middleware system that goes in, handles all the incoming requests, immediately responds to the app saying, your request is queued, check back later. Simple HTTP API. Then it queries the databases very slowly, not very slowly, I mean in whatever manner the database can handle, and the results are written to a results DB. Now the results DB is an ephemeral storage. The results come there, the app pulls the results from the results DB directly and you're done. So the app never interacts with the large slow DBs. Even if you have 1 million requests coming in, it won't overload the database because there's traffic control happening there. So that system is called DungBeetle. Now DungBeetles are insects. There are many different kinds of DungBeetles. What's cool about them is that they're tiny little beetles, but they roll dung, feces. Now I'm not implying that data in databases is garbage or dung. That's not that. But these are tiny creatures that can move dung like 1,000 times plus their body weight. So the tiny little things that can move a lot of mass. So that's why we named this small little middleware system DungBeetle. So it's a simple app. It's a very lightweight single binary app written in Go. And it's distributed by nature. You can run many copies of DungBeetle that do traffic control, handle all your requests. And it helps applications completely separate out their SQL or large data reporting layer out of it. So quickly diving into how it works. Like I said, the architecture is really simple. The concepts are really simple. It's a hack that we've stitched together. So imagine you have a financial application and you generate n kinds of different reports. Each report is defined as an SQL query and it has a name. You'll see that, get profit entries by date. So every report is an SQL query. It's defined in a file. It has a name. And you can have some additional parameters like DB saying this query should be executed against this DB. So each of these is a task. Then you have a job. So when the app has to generate a particular report, it sends an HTTP request, super simple HTTP API to DungBeetle, which is running. You'll see that it's the curl request is going to the job, the SQL query that was named here. Same thing, get profit entries by date, get profit entries by date. And the parameters that is required for the SQL query, it's passed there. And when you make this request, DungBeetle immediately queues that job somewhere and returns a status. Now the app is free to poll DungBeetle for this for the status of this job. Is it pending? Is it complete? Sometimes it might take 5 seconds. It could take whatever. It's arbitrary. We're not concerned about how long it takes for a particular job to complete. It all depends on the capacity of the database. So when a job is complete, that is when an SQL query has finished executing, that produces results for the particular report, it goes into a results database. And the app now simply has to do a select star on the results database. Now the interesting hack, I think this is the biggest hacky aspect of this particular hack. Every single job that is completed, that is every single query that finishes executing, its results are written to a brand new table in the results DB. So when I, as a user, go and click on get my financial report, the results go via this async thing and it's written to a table in this DB. When another user goes and pulls the same report, it's written to another table. So if you have millions of users pulling millions of reports, each result is written to a whole different table that is freshly created for that particular report, for that particular user. And do you know that the results are generally small? Your bank statement will have 5, 10, 500 or 10,000 things, right? So after scanning hundreds of billions of rows, the responses, which will be a bunch of rows that go to this dedicated table, and the app simply does a select star on it, which is instant. So we chose Postgres as the results DB. Now, when we started out, we didn't really know the extent of this hack or how far it would go. We started using this approach, I don't know, 5, 6 years ago. People would pull, few 10,000 reports a day, no more. And we'd see Postgres end up with 10,000 tables, 50,000 tables, 1 lakh tables. And that was a curious thing to observe. Then it grew to 500,000 tables. Then it grew to 1 million tables. Because every report that is pulled on the financial platform ends up as a fresh Postgres table. Then we one day ended up with, I think some 11, 12 million independent tables in a results Postgres database. And so when I submitted this talk title, I think I had 5 in the title. Then I figured that, no, that number is outdated. So I got it changed to 5 plus. Then I figured that over the last several months, the average number per day is 7 million. So I got the talk title changed again. Then the organizers asked me, do you want to change it again? Are you working on increasing the number of Postgres tables in the last 48 hours? But the thing about stock markets is that it's entirely unpredictable. Tomorrow there could be one big event and we might end up with 20 million tables. So 7 million is what we see on average. Now, somebody outside just now was asking me, are you talking about 7 million rows in a table, or are you talking about 7 million tables in a Postgres database? So it's 7 million Postgres tables. But why, right? I mean, the thing is, why not? If Postgres works beautifully, why not? It works. And this is such a simple hack, and it allows us to scan our massive, 500 billion rows of financial data and deliver reports to users instantly on a daily basis without overloading the data and handling a bunch of headache. Now, the other cool thing is, typically once a user pulls a report on a platform, they do further operations on it, sort it, filter it, etc., etc. So once you have a cached results table, you can do all those subsequent operations on it, completely eliminating the backend database from handling that load. So that's some stats. We have a single Postgres node running on a single EC2 instance, it's an ephemeral throwaway DB. So it has 64 vCPUs, 128 GB RAM, and on an average random day, that database has 7 million tables. Each table has different kinds of columns, different kinds of rows. Some reports only have two columns, some have 10, 50. So PG attribute is a meta table inside Postgres that stores information about columns in a table, in every single table. Now, because we have 7 million tables, and all 7 tables have completely different column structures, that table is 48 GB. So just the metadata of this database on this random day is 60 GB. Now, one would assume that when you, let's say, restart Postgres, it has to scan all the metadata stuff and it'll take forever to boot. It doesn't. This database instance, when we restart, it comes back up in like 3 seconds. Now, that is a testament to Postgres' battle-testedness. So, the other cool hack is, this is a throwaway DB, right? User pulls the report. We can throw the cache away at some point. So we do it overnight. But the thing is, you can't do a drop table. You can't scan the tables. Those operations won't finish. So the simplest thing is to shut down Postgres, detach the disk, attach a fresh disk, and bring it back up. That whole thing, that hack also takes just like a few seconds. So we reset all of this every night. So DungBeetle, like I said, it's a concurrent distributed system with multi-threaded concurrent distributed system. You can run multiple instances of DungBeetle as a program in a bunch of places. Some reports are very heavy. They take seconds to generate. Some are generated in milliseconds. So you can create separate queues and send the request for those heavy reports to those particular queues where you have, let's say, 10 instances of DungBeetle running. Or you can send lightweight queries to another queue where you just have 2 instances. You can do all of these things. But the entire program is just like 1,700 lines of Go code. And like I said, it's a really simple hack, but it works at scale. So I have a screenshot there, which is another trick that we employ. So these were reports, right? We have hundreds of such reports, like really complex reports. And each report is an SQL query, and each SQL query can produce arbitrary columns, 2 columns, 10 columns, 15 columns, it doesn't matter. And they can all be of different types. So how do we map those types to the results table that is created in the separate results cache? It's a super simple type map like that. If the report is being pulled from a Postgres database, you can iterate through the columns in your database driver and figure out the column type and then map it to the target results database. We've used Postgres as our target results database, but it can be anything. You can pull data from ClickHouse and cache it in Postgres. So it's just a super simple type map that enables this. And that's a DungBeetle rolling dung, which is feces. And that's Postgres. So this whole thing, this whole hack, this whole project, the way we scale reporting at Zerodha, it's all dedicated to Postgres. And like I said, it's a testament to how amazing a piece of technology Postgres is. And with that, I finish. Thank you.